way to learn about physics, then we have just the thing.
Clayton Clark is live at Fresno State, raising his IQ, which is, I think, impossible. I mean, it's way up there with the physics department. Good morning, Clayton.
Good morning, Kim and Kopi. It's going to be tough, but we're going to try to get my IQ at least 1 point higher this morning. We're with the Fresno State Physics Department, and they're great about going out in the community and teaching you how fun physics can be and kind of teaching us the science behind a lot of the things we see every day. And so we have another professor with us today. Karl is going to teach us how the science behind tuning instruments, right?
Okay, yeah, we're talking about oscillations today. Oscillations, and we're going to start with a xylophone tone and move on to pendulum.
Okay, so explain what the xylophone can teach us.
Well, here, hearing is believing. We have beautiful sound, and then we have to understand that there's a vibration going on. It's too fast for us to really see the things vibrating up and down, and eventually our eardrums are vibrating. Okay, so as physicists, we want to simplify things, and we hang a bowling ball from a string, and now we're going to have a very slow vibration, push this thing out of equilibrium, and we can count. 1, 2, and so that's the frequency, the number of times it oscillates per second. So our students are busy studying this right now as we speak, and the first thing they learn about the pendulum is that you can make the pendulum smaller, and it'll have a higher beat, or actually a higher oscillation frequency, as you can see right there. 1, 2, 3, 4. So there's a higher frequency.
So we're talking about music beats here, sort of.
Well, this is a tone that maybe a blue whale could hear. I'm making that up. Okay, it's a little bit too low of a frequency to hear, but some gigantic animal maybe.
All right.
Okay, so let's go ahead and see why I brought 2 pendula instead of just 1. I'm going to connect this with a spring. Okay, there's one connected to the other. And there's actually nothing different. These were identical pendula. If I pull them and let go like this, they just swing back and forth with the same frequency. But if I want to bring the spring into the action, I give it a pull this way, and they go against each other slightly faster. These are all subtle differences in the frequency. We're not hearing it, so to speak, we're seeing. But I'm now going to pull one and leave the other one at rest and release it, and we're going to see a new effect.
Okay, so that one was moving, now it's stopped, and that one's moving.
Dead stop. Now
this one's starting to stop, and that one's moving.
You got it.
Now, is there a more scientific explanation than what I just said?
Well, we call that the phenomenon of beats, and we have 2 oscillations going on here. We have the individual ones, and we have the collective one that's sloshing back and forth, so to speak. And I drew a graph of what's going on right there. And we started out with the first one, we're going to call it number 1 here. It started out at full amplitude, came to a dead stop. Full amplitude, came to a dead stop. And all the while, it's going rapidly. Okay. Now, the second one is doing something similar but out of phase. So this one started at rest, reached a peak when this one is at 0. Okay.
All right, and all that right there explains beats. Now you know the science behind what it's like tuning your guitar when you're at home jamming, Kim and Kopi.
Awesome.
Well, let's do a tuning.
You know, to me, it looks like 2 fish kissing, the top one. And just a thought.
It's 7:16. Let's celebrate some great day birthdays now.